All right, let's jump right into this explainer and demystify the mathematical magic that literally keeps our modern automated world from spinning out of control. Look, whether you're an engineering undergrad studying for your GATE exams, a dedicated researcher, or honestly just someone fascinated by modern control systems, wrapping your head around the Nyquist plot is absolutely foundational. Today, we're going to break down this complex plane analysis using intuitive concepts and real-world applications so you can see exactly how we predict system stability. We've got a pretty packed agenda today. We're going to start with the quest for system stability, then map the complex plane, define the Nyquist stability criterion, compare open versus closed-loop systems, look at measuring relative stability, and then wrap the whole thing up with real-world engineering applications. Let's get right into it. Section 1, the quest for system stability. Let's ground this in the real world real quick, because catastrophic failure is a massive risk if we don't have active stability control. Think about an aircraft autopilot, an electric vehicle control system, or a satellite up in orbit. Actually, to give you a specific example, a spacecraft with a specific inertia ratio, where I3 is greater than I1, has an inherently unstable Earth-pointing orientation. Without flawless active feedback control, that spacecraft would just violently tumble out of its orientation. Whether we're talking high-speed robotics or massive power grids, if the closed-loop system goes unstable, the physical hardware fails. It's really that simple. And this perfectly illustrates our problem solution framework here. To ensure stability, engineers have a few mathematical tools at their disposal. You've got the root locus method, which focuses on finding the exact closed-loop poles. But man, for highly complex systems, or systems where you only have experimental data, that can be mathematically exhausting, if not totally impossible. That is exactly why we turn to frequency response methods. Tools like the Nyquist plot are incredibly powerful because they let us determine absolute closed-loop stability just by looking at the open-loop frequency response. We completely bypass the headache of calculating those exact closed-loop poles. Moving on to Section 2, mapping the complex plane. Okay, so conformal mapping. This is basically a mathematical process where a contour in our original domain, the S-plane, maps directly into a new plane, like the f of s or LFS plane, while keeping all of its intersection angles intact. The entire Nyquist stability criterion is built on a concept from complex variable theory by a mathematician named Cauchy. Cauchy's theorem essentially says that if we draw a closed path in the S-plane, we can map that exact path through our transfer function to see what kind of wild shape it creates in a totally new mathematical plane. So to actually construct the Nyquist path, we step-by-step enclose the entire right half of the S-plane. Why the right half? Well, because any pole that lands on the right side of the S-plane means our system is totally unstable. Step 1. We sweep up the positive imaginary axis, testing all frequencies from 0 to infinity. Step 2. We take this massive, infinite semicircular sweep to capture literally everything on that right side. And step 3, we move right back down the negative imaginary axis, which gives us a perfect mirror image. Oh, and if there are any poles sitting exactly at the origin, we just take these infinitesimal, tiny little detours around them so the math doesn't completely break down. All right, Section 3, the Nyquist stability criterion. Here is the absolute crux of the entire methodology. We've run our frequencies, we've done the math, and we've drawn this massive dynamic contour on our mapped plane. But what are we actually looking for? We're looking for a very specific intersection on this mapped plane to answer our ultimate question of stability. And that crucial coordinate is -1 plus j0. This single point on the complex plane is the critical point that dictates system survival. But why this exact spot? Well, the formula for a closed-loop transfer function has a denominator of 1 plus the open-loop transfer function. If that open loop equals exactly -1, the whole denominator becomes 0. And you know what that means? Our system output shoots to infinity. It blows up. Which brings us to the magic formula, z equals p minus n. A feedback system is stable if, and only if, z equals 0. Let's break that down. Z is the number of unstable closed-loop poles. P is the number of unstable open-loop poles, which honestly we usually already know going in, and n is what we're physically counting from our visual plot. It's the number of counterclockwise encirclements of that critical -1 plus j0 point. If the number of counterclockwise encirclements perfectly offsets any positive open-loop poles we started with, z drops to 0, and boom, our system is perfectly stable. Section 4, open versus closed-loop systems. So we map the open-loop behavior to definitively count the closed-loop poles hiding out in the unstable right-half plane. Think of open-loop dynamics as your raw materials. They're measurable right there in the lab,
And we can easily inject a variable gain, which we represent with k, just to see how the system reacts. Closed-loop dynamics, on the other hand, represent the final, fully assembled machine. It's way harder to model directly, but it's the closed loop that ultimately dictates if your final automated system is going to hum along smoothly or just oscillate completely out of control.
There's a really brilliant analogy for this. Imagine the Nyquist plot expanding like a balloon as we increase that variable gain, k. Gain k is just a multiplying factor. If you crank up the gain in a simulation, like in MATLAB or Simulink, the actual shape of your Nyquist contour doesn't change, but the size does. It inflates. If you decrease k, it shrinks. Your system crosses that mathematical boundary from stable to unstable the exact millisecond that inflating balloon expands enough to swallow up our critical -1 plus j0 point. Let's hit section 5, measuring relative stability. Now, just being stable isn't really enough in the real world. We need a safety buffer. First up is gain margin. Think of this as telling an engineer exactly how much they can crank up the power, or the gain, before the system's Nyquist plot hits that critical -1 point and goes totally unstable. You measure this precisely where the plot crosses the negative real axis, meaning the phase angle is exactly 180 degrees. If your gain margin is super tight, even a tiny, unexpected spike in amplification could crash your whole system. Then we have phase margin, which is basically the other side of that safety coin. It acts as a sort of shock absorber against time delays. It measures how much phase shift the system can tolerate before the plot rotates right into that critical point. You measure this exactly where the contour intersects the unit circle, which means the system gain is at unity, or exactly 1. Tools like the Nyquist chart and modern software rely on these exact margins to guarantee robust control design. A system in the real world has to deal with constant physical unpredictability, stuff like unmodeled friction, sudden temperature changes, or signal transport lags. By maintaining healthy gain and phase margins, engineers basically ensure that even if the real-world system behaves slightly differently than the idealized math model, it's not going to cross over that invisible line into instability. And finally, Section 6, Real-World Engineering Applications. You say, this isn't just some abstract theory you cram for an exam. This is literally the operating code of our modern infrastructure. From the disk drive reading your data with hyper-precise track positioning to the steam valve spinning a massive power plant's turbine generator, these mathematical mapping techniques are running the physical systems of our everyday lives. When a DC motor speed controller in an EV adjusts to changing road friction, or an industrial robot arm moves with pinpoint accuracy without shaking itself apart, it's happening because an engineer properly mapped the Nyquist contour and made absolutely sure the phase and gain margins were heavily protected.
Which leaves us with a pretty fascinating final thought. Harry Nyquist developed this frequency domain stability criterion way back in 1932. And today, almost a century later, we are using that exact same map to keep spacecraft from tumbling out of orbit and modern EVs safe on the highway. It really makes you wonder about all the other hidden mathematical architecture that's keeping everything around us in perfect, stable motion. Thanks for hanging out with me for this explainer. Keep exploring the math, and keep questioning the limits of our automated world.